Astronomers first catalogued NGC 520 in the 18th century, but only modern detectors revealed why this object earned the nickname train wreck. It is not a single serene spiral but two disk galaxies in the midst of a high-speed collision roughly 100 million light-years away. Through an optical telescope the pair looks like a warped spindle bisected by a dark lane. In the infrared and radio, the picture changes completely, exposing rivers of cold gas funneled toward two buried nuclei and a star-forming furnace ignited by gravity itself. The train wreck's dust is so thick that vast nurseries of newborn stars are hidden from visible light, glowing instead at far infrared wavelengths where heated grains re-radiate the energy of thousands of embedded clusters. The wreck's geometry tells a dynamical story. Each galaxy brought in a rotating disk of stars, gas, and dark matter. Tidal forces have torqued those disks, flinging out long, faint tails of starlight while throwing the inner gas off balance. Much of that gas has lost angular momentum and spiraled toward the centers, piling up in a compact region between the two cores. In that cramped volume, shock waves, cloud collisions, and compressed magnetic fields accelerate the conversion of gas into stars, pushing the system's star formation rate to levels an order of magnitude above a normal spiral. Observers pick up the signatures of this overdrive as bright hydrogen recombination lines, copious infrared luminosity characteristic of a LIRG, and winds of ionized gas that vent perpendicular to the main dust lane. Seen edge-on, the merger pair looks deceptively simple, but spectroscopy resolves two distinct nuclei separated by only a few thousand light-years, each moving at a different velocity. These are the surviving hearts of the original galaxies, still orbiting one another as dynamical friction saps their energy. Around them, swarms of massive, blue star clusters, some only tens of millions of years old, trace where tidal shocks have recently swept through. X-ray observations reveal point sources consistent with ultraluminous X-ray binaries, the expected byproducts of starburst episodes in which massive stars live fast, die as supernovae, and leave behind black holes that gorge on companion winds. The system's cold gas reservoir is the real fuel line. CO mapping shows dense molecular complexes wrapped around the central kiloparsecs, while extended HI plumes mark where the outer disks have been shredded. Numerical simulations tuned to the train wreck's kinematics reproduce its crooked dust lane and asymmetrical tails when the two progenitors meet on an off-center, slightly inclined orbit, a configuration that explains why one disk looks more mangled than the other. In this picture the colliding duo is in a mid-stage encounter, past first close approach, well into the starburst phase, and still some hundreds of millions of years from final coalescence. Despite the chaos, the physics is remarkably orderly. Gravity orchestrates the inflow, turbulence and shock set the cloud mass spectrum, feedback from supernovae and stellar winds regulates but cannot quench the burst, magnetic fields thread the gas and help guide outflows along the minor axis. The result is a galaxy-wide laboratory for feedback loops. Young stars stir the medium that will birth the next generation, while outflows seed the circumgalactic surroundings with metals that later rain back in. The remnant to be will not resemble either parent. When the two nuclei finally merge, violent relaxation will scramble stellar orbits into a hot, pressure-supported distribution, erasing the tidy rotation of spirals and building an elliptical-like body surrounded by fossil tidal shells. The train wreck is also a time machine. Nearby enough to dissect in detail yet far enough to offer a global view, it stands in for countless ancient collisions that, at higher redshift, were the norm rather than the exception. Where we resolve dust lanes and clusters here, telescopes looking deeper into space record the aggregate light of many such smash-ups that built today's massive galaxies. The battered pair, the starburst engine, the winds rising off the plane, the draped HI streamers, each feature knits into a cosmological narrative in which mergers assemble mass, trigger central growth, and reshape galactic architecture. Call it the wreck, the merger, the colliding duet, the double-cored starburst factory, whatever the label, the essential draw is the same: this is gravity at work in real time. Watch long enough, and the crooked spindle will round out, the dust lane will disperse, the tidal tails will fade into ghostly arcs, and a new, redder galaxy will glide where two once struggled. For now, the system sits mid-transformation, burning bright in the infrared, crackling in X-rays, and throwing out tidal signatures like sparks from an anvil, a vivid reminder that galaxies are not static islands but evolving ecosystems driven by encounter and change. Peering deeper into the battered duet, astronomers find that obscuration is the rule rather than the exception. The densest dust sits like a tar-black sash across the midsection, where supersonic streams of molecular gas smash together and collapse into clusters. Millimeter-wave maps trace the carbon monoxide that betrays this cold reservoir, showing knots and filaments wrapped around both cores and braided between them. Where shocks bite into these filaments, line ratios jump, turbulence broadens the profiles, and cloud lifetimes shrink, from leisurely tens of millions of years in quiet spirals to brief, frantic episodes measured in a few million. The shattered spindle is, in effect, a galaxy-scale compression machine. The broken pair's starburst leaves fingerprints across the spectrum. In the ultraviolet, swarms of hot, short-lived O and B stars carve bubbles into their natal cocoons. In the optical, H-alpha stitches a neon-red embroidery along the dust lane's ragged edges, where ionization fronts creep through the rubble. In the mid-infrared, polycyclic aromatic hydrocarbon features flare as small grains vibrate under intense radiation, while the far-infrared continuum surges as larger grains store and re-emit stellar energy. Pushed to radio wavelengths and a hushed chorus of synchrotron whispers from supernova-accelerated electrons reveals where massive stars have already died, turning the wreck into a chronograph that registers both newborns and their recently fallen elders. Spectroscopy separates the two hearts of the colliding duet not only in position but in motion. Each nucleus carries its own rotation curve and metallicity pattern, hints of distinct pasts now being erased. One core appears slightly more shrouded, with deeper extinction and a richer molecular budget, the other shows clearer sightlines punctured by chimneys where feedback has punched through. Between them, a bridge of shearing gas hosts superstar clusters, compact swarms so massive and dense that some will survive as globular clusters in the future remnant, fossilizing the starburst's most intense moments as long-lived stellar cities. The mangled spindle is not quiet on large scales, either. Tidal tails arc away like ribbons torn from the outer disks, each a dynamical seismograph of the encounter geometry. In their faint light, observers find redder, older stars mixed with sprinklings of blue knots, star formation kindled where tidal shocks have scraped gas into temporary eddies. HI mapping stretches these tails even farther than starlight suggests, revealing ghostly plumes of neutral hydrogen that will, over gigayears, either rain back to rebuild a halo or be siphoned into the intergalactic medium. The train wreck is thus both forge and foundry, minting metals in its core while exporting enriched material to its outskirts. Amid the fireworks, the central engines sleep lightly. Unlike some mergers where a gaping quasar dominates, the double-cored furnace shows, at most, weak signs of accretion, low-level, flickering activity that struggles to compete with the blaze of star formation. That balance is temporary. As orbital energy continues to drain away via dynamical friction, the nuclei will spiral inward, and the inflow that now feeds clusters will increasingly funnel to subparsec scales. When the two supermassive black holes finally pair and coalesce, the newborn single engine may light up, and, on a timescale impossibly long to human observers but brisk to galaxies, the remnant will broadcast a burst of low-frequency gravitational waves into the cosmic web. The colliding corral also tests how galaxies regulate themselves. Feedback from supernovae and stellar winds pressurizes the interstellar medium, building hot superbubbles that merge into fountains and winds. X-ray mosaics pick out these overpressured cavities, optical Echelle spectra catch their outflowing skins, radio continuum maps trace magnetic fields stretched into streamers that help guide charged particles out of the plane. Too much feedback, and the starburst quenches, too little, and gas collapses too quickly and smothers itself. The bruised pair rides that knife edge, converting gas with remarkable efficiency while still venting enough energy to keep the engine from stalling. Numerical experimentation fills in what telescopes cannot watch in real time. Simulations tuned to the crooked dust lane and the misaligned tails reproduce the scene when two disk galaxies of moderate mass approach on an inclined, off-center orbit with a small but non-zero impact parameter. First passage twists the disks, launches the tails, and drives the initial inflow. A long, looping dance follows, with paracentric kicks that reignite inflows and grow the central starburst. Frame by frame, the models show stellar orbits being scrambled by violent relaxation, the original spiral patterns dissolving into a spheroid supported by random motion, a plausible destiny for this train wreck once the last sparks fade. Because the wreckage is close enough to resolve, it calibrates what high redshift surveys must infer in bulk. At early epochs, when gas fractions were higher and encounters more common, galaxies like this bruised duo were not exotic, they were the workhorses of assembly. The obscured star formation we tally here, with dust converting ultraviolet light into infrared glow, echoes the cosmic infrared background that encodes much of the universe's hidden stellar growth. In that sense, the broken pair is a Rosetta Stone for a noisier epoch, translating small-scale physics, shocks, turbulence, cloud fragmentation, into the grand grammar of galaxy evolution. Even the dark sector leaves subtle signatures on the smashed duet stage. The shapes and extents of the tails, the persistence of warps, and the timing of orbital decay all depend on the mass and profile of the halos that enfolded the progenitors. By fitting the tail's curves and the nuclei's slowdown, dynamicists infer how much unseen matter cushions the encounter, how it flexes, and how it absorbs orbital energy. The result is a reminder that every bright flare of star formation rides within a vast, invisible scaffold of dark matter that choreographs the dance. Call the system the wreck, the shattered pair, the colliding furnace, the double-chord metamorph, the crooked spindle, the names keep pace with the spectacle. What anchors the fascination is the feeling of immediacy, gravity mid-sentence, riding in dust and fire. Follow the arc forward and the tail bends toward a reddened, smoother remnant with faint shell-like memories of its violent youth. Look backward and you see two ordinary disks, gas-rich and unsuspecting, about to discover how encounter turns structure into story. As the shattered duet drifts through cosmic time, its environment also shapes the performance. NGC 520 does not float in isolation, it inhabits a loose group of galaxies where occasional flybys and faint gravitational tugs stir its outskirts. This neighborhood provides additional gas to draw in and amplifies the violence of the central merger. Observers spot faint companions in its vicinity, some showing tidal signatures of their own, reminders that the train wreck's upheaval is part of a broader cycle of growth and destruction that governs entire groups of galaxies. The wreck starburst is not only a fireworks display but also a chemical factory. Every supernova triggered by the collision sprays heavy elements, oxygen, silicon, iron, into the interstellar medium. Within tens of millions of years, these metals seed future generations of stars and planets. Infrared spectra reveal emission from silicate grains, carbonaceous compounds, and even crystalline dust freshly forged in stellar deaths. What is chaotic on the scale of stellar populations is constructive on the scale of cosmic chemistry, enriching the surrounding medium and altering the composition of whatever stellar systems form next. Future telescopes sharpen the picture further. Instruments tuned to millimeter wavelengths trace the dense cores of molecular clouds on the verge of collapse. Adaptive optics on ground-based giants pierce through veils of dust to separate compact clusters, some only a few parsecs wide. X-ray observatories reveal diffuse halos of hot gas swelling around the wreck, energized by collective winds. Each band highlights a different facet of the train wreck's drama, and together they confirm the same conclusion: the system is a furnace in transition, consuming its fuel at breakneck speed while preparing to transform into something new. For theorists, the crooked spindle is a benchmark case study. Simulations must not only reproduce its dust lane and double nucleus but also account for its starburst luminosity, outflow energetics, and tidal debris. By adjusting orbital angles, mass ratios, and gas fractions, modelers tune their codes until virtual galaxies resemble the observed wreck. When they succeed, they gain confidence that the same physical recipes apply across cosmic history, from the local group's quiescent dwarfs to the ultraluminous infrared galaxies that blaze at high redshift. To casual stargazers, the battered galaxy looks like a scar across the heavens, but in reality it is a portrait of creation through destruction. Its two progenitors sacrificed their spiral forms, yet from their wreckage will rise a massive, evolved system that carries forward their combined mass, metals, and history. For the next few 100 million years it will remain a spectacular train wreck, glowing in infrared, echoing with supernovae, and trailing long arcs of stars, but eventually it will quiet, round out, and merge its two hearts into one. In that sense, the broken pair is both epitaph and prologue, a closing chapter for two spirals and the opening of a new story written in the language of gravity, gas, and light. In the battered duet's inner few kiloparsecs, pressure piles up to starburst city levels, and the gas behaves less like a quiescent disk and more like a storm front. Cloud lifetimes shrink, collapse becomes cascade rather than trickle. The double-core starburst engine throws off age gradients you can read like rings in a tree. Very young clusters girdle the dust lane where compression is strongest, older blue knots pepper the bridges and inner tails from earlier bursts, and still older, redder populations trace the pre-collision disks. This layering preserves a timeline of impacts and pericentric passes, letting astronomers reconstruct the choreography that twisted two quiet spirals into one crooked spindle. Magnetic fields thread the wreckage and leave their own signatures. Polarized radio maps reveal ordered strands stretched along the primary dust lane and draped into the outflows, as if the field lines have been combed by shear and then lofted by rising bubbles of hot gas. Those fields matter. They help confine cosmic rays, cushion shocks, and steer charged particles out of the plane, shaping the faint radio halos that crown the colliding furnace. Where turbulence shreds order, depolarization deepens, drawing a cartography of chaos that aligns with the brightest H-alpha filaments and the widest CO lines. Chemical evolution in the shattered pair is already measurable. Supernovae from the first wave of massive stars seed the central kiloparsec with oxygen and silicon, flattening metallicity gradients that once ran cleanly across the progenitor disks. Dust grows quickly in this enriched stew. Silicates and carbonaceous grains coagulate in dense pockets, changing the extinction curve so that the mid-infrared brightens even as optical light remains strangled. In the same regions, nascent clusters reach masses of 100,000 suns and more. A fraction will harden into globular cluster survivors, future fossils that remember the train wreck's brief, incandescent youth long after its tidal tails fade. Kinematics tell the rest of the tale. Long-slit and integral field spectra disentangle multiple velocity components along nearly every sightline through the central lane, rotating streams from each progenitor, shocks with flipped gradients where gas collides head-on, and vertical chimneys with speeds high enough to escape the disk if not the halo. The neutral hydrogen envelope, more extended and more easily perturbed, fans into asymmetrical plumes whose curvature encodes the impact parameter and the sense of spin-orbit coupling. Fit those arcs, and you retrieve the initial conditions, a slightly inclined, off-center strike that traded angular momentum for heat and sparkle. Compared with poster-child mergers like the antennae, this bruised duet is more heavily veiled and more compact in its star-forming core, a reminder that not all collisions stage their drama in the clear. Much of the action here is clandestine, whispered in millimeter lines and mid-infrared features rather than shouted in UV knots. Yet the energy budget is enormous, luminosity solidly in the luminous infrared regime, mechanical power in the outflows sufficient to punch superbubbles through the disk, and a momentum flux that lifts metals into the circumgalactic medium where they cool, drift, and may one day drizzle back as fresh fuel. The double nucleus phase is a fleeting chapter on galactic timescales. Dynamical friction keeps shaving orbital energy, bringing the cores closer with every pass. Tidal stresses will keep stoking inflows, but the fuel line is finite. As gas turns into stars or escapes in winds, the blaze will dim. Then comes coalescence. Violent relaxation scatters stellar orbits into a spheroid, shells and ripples ripple outward as phase-wrapped memories, and the newborn remnant will rotate slowly, supported by pressure rather than by a thin disk's grace. Where the crooked spindle once cut the sky, a rounder, redder body will take its place, quieter, heavier, and chemically richer. Even at this turbulent peak, the colliding metamorph is an educator. It teaches that galaxy growth is not smooth but punctuated, that dust can hide, but not erase, the engines that build stars, that magnetic fields and feedback are not footnotes but co-authors of morphology, that dark matter's invisible hand sets the tempo of decay, and that what looks like ruin is often the shortest path to renewal. Name it the wreck, the broken duet, the starburst anvil, the double-chord chrysalis, the labels change, the lesson doesn't, gravity writes in fire and dust, and galaxies learn to read. The chaotic duet also offers a rare laboratory for watching black holes approach one another long before the final plunge. Each nucleus harbors a central massive object, and although neither blazes as a full quasar, subtle X-ray flickers and mid-infrared excess hint at low-level accretion. As inflowing gas continues to funnel inward, these hidden engines may awaken, first as obscured active nuclei and eventually as a single, brighter beacon once the two cores merge. That merger, in turn, will send a burst of gravitational waves rippling through spacetime, a whisper too deep for present detectors but exactly the kind of signal future low-frequency observatories are being built to catch. Thus the shattered pair is more than a spectacle, it is a prediction, a prelude to a cosmic broadcast that will one day confirm how galaxies and black holes co-evolve. Even at the stellar level, the wreck is rewriting its population. Massive clusters born in the dusty midplane will evolve quickly, producing supernovae within tens of millions of years, peppering the surrounding gas with shockwaves and heavy elements. Smaller, denser clusters may survive the chaos to become long-lived globulars, orbiting the eventual remnant as ancient witnesses. Wide-field images already reveal hundreds of such compact knots strung like beads along the tails and bridges. Their distribution is not random. It maps where tidal forces compressed gas pockets into burst factories, each cluster a frozen imprint of gravitational stress. The train wreck's tidal debris stretches far into the darkness, beyond what casual stargazers can see. Sensitive surveys uncover faint arcs of stars and hydrogen stretching tens of thousands of light-years from the center. Some of these features curve back toward the system, destined to rain down again and feed the halo, others may drift away, carrying whole populations of stars into intergalactic exile. If captured by nearby companions, these streams could seed satellites or be cannibalized into foreign halos, spreading the fingerprints of the merger far beyond the immediate wreckage. In cosmological context, this disordered spindle is a reminder of how common such events are. The universe at redshift 2 or 3, the so-called cosmic noon, was crowded with similar collisions, only at that distance we see them as faint smudges in deep surveys. By examining the broken pair up close, astronomers can decode what those faint smudges really represent: furious starbursts, tangled dust lanes, doubled nuclei, and tidal plumes stretching across intergalactic space. Each detail sharpened here becomes a calibration point for interpreting the early universe, where countless galaxies grew up through precisely these kinds of violent unions. The crooked spindle is therefore both singular and archetypal, singular in its peculiar dust-laden visage, archetypal in its role as a merger caught mid-stride. Its present is turbulent, its future predetermined, the double heart will fuse, the dust will thin, the blaze of star formation will cool, and the remnant will settle into the ranks of massive, reddish galaxies that populate today's cosmic neighborhoods. Yet the drama of its current form ensures that, for those who observe it now, the wreck is unforgettable, a living manuscript of galactic transformation, written not in words but in dust lanes, shock fronts, and starlight. On the smallest scales the wreck behaves like a laboratory for clustered star birth. The most compact knots pack tens of thousands of suns into volumes only a few parsecs across, and their light functions follow the telltale power law slope associated with superstar cluster factories. In the bridges and inner tails, slightly looser associations trace where shocks have swept up gas into feathered ridges and then fragmented. The initial mass function of the newborns appears unremarkable despite the turmoil. Gravity and cooling still carve out familiar stellar demographics, yet the clustering is extreme, tilting the census toward bound systems robust enough to survive for billions of years as a new generation of globulars surround the eventual remnant. Look at the smashed spindle through diagnostic lines and it reads like a spectrography textbook written in dust. Balmer emission marks the photoionized H2 zones around the youngest clusters. Low ionization lines strengthen along shock fronts where clouds ram together at supersonic speeds. Molecular hydrogen glows where turbulent dissipation warms dense gas. Plot those ratios on classic excitation diagrams and the point sprawl from pure star formation into shockated regimes, a cartography of energy sources braided through the midplane. Mid-infrared features from aromatic molecules wax and wane with radiation hardness and grain processing, while long-wavelength continua chart the heat budget of the cloak that hides so much of the action from optical eyes. Kinematically, the colliding furnace is a masterclass in decoupling. Gas streams inherited from the progenitors interpenetrate with mismatched spins, some lanes shear past one another in counter-rotation, setting up Kelvin-Helmholtz ruffles along their boundaries. Where torques are strongest, inflow stalls and piles into rings that resemble the skeletal beginnings of a bar, even though the original disk symmetries are wrecked. Vertical chimneys vent above and below the main dust sash, carving conical cavities whose rims sparkle in recombination light. Outside, the neutral hydrogen envelope records every tug and twist as long, low-surface brightness plumes whose curvature encodes the encounter's off-center strike. The broken duet's metal economy is already booming. Each supernova flash salts the surrounding medium with fresh oxygen, magnesium, and iron. Dust grains nucleate and grow in the enriched turbulence. Radiation pressure and hot superbubbles load those metals into outflows that climb into the circumgalactic halo. Some of that freight will cool and fall back, building a fountain cycle that prolongs star formation. Some will escape the system entirely, seeding the group environment with material that future dwarfs and streams will inherit. In this way the train wreck rights beyond its borders, turning a local starburst into a neighborhood enrichment project. Comparisons anchor its place on the merger spectrum. It is more buried than the flamboyant antennae, less compact and extreme than the ultraluminous engines typified by ARP 220, but firmly in the family of mid-stage encounters where double nuclei, dusty inflows, and elevated infrared output go hand in hand. That placement matters because theory calibrates itself against such benchmarks. Mass ratios, orbital tilts, gas fractions, and feedback prescriptions must conspire to reproduce not only the morphology but the luminosity, wind energetics, and cluster demographics of this crooked spindle. When simulations nail the dust lane's kink and the tail's asymmetry, they also tend to recover the observed burstiness and outflow geometry, evidence that the recipe is close to right. The future reads clearly in the present. Dynamical friction keeps bleeding orbital energy from the twin cores. The inflow that now favors clustered youth will tighten its focus towards sub-parsec scales. The two central black holes will pass from mutual orbit to bound pair to coalescence. Violent relaxation will then heat the stellar orbits into a pressure-supported spheroid, while phase wrapping will leave faint, shell-like fossils around a rounder, redder body. The flamboyant dust sash will thin, the infrared blaze will fade, the tails will dissolve into ghostly arcs, yet a halo of hardy clusters will continue circling, silent archivists of the wreck's incandescent youth. And still, the lesson of the colliding chrysalis is larger than one system. It demonstrates that galactic growth is episodic rather than smooth, that dust can hide the engines of change without diminishing their impact, that magnetic fields and turbulence are co-authors of morphology, and that the invisible scaffold of dark matter sets both tempo and trajectory. Call it the train wreck, the crooked spindle, the starburst anvil, the double-chord metamorph. By any name it shows how encounter becomes transformation, how destruction becomes structure, and how gravity writes its longest sentences in the ink of dust and starlight. Zoom out and the fractured spindle still resolves into crisp components you can weigh in time. Stellar population fitting dates the youngest knots to only a few million years, while clusters in the bridges and inner tails peak around a few times 1010 years, timestamps for the last paracentric passages. Gas diagnostics put midplane pressures hundreds of times above those in calm spirals, line widths broaden to tens, over 100 km/s where shocks bite, and outflowing skins climb to a few hundred km/s along the minor axis. The infrared luminosity lands squarely in the luminous infrared regime, a shorthand for how efficiently the cloak of dust is turning UV from massive stars into heat and long wavelength glow. Radio maps finish the census of fuel and fallout. Neutral hydrogen fans into uneven plumes that extend well beyond the starlight, sketching the original disk's edges and the encounter's off-center hit. CO lines trace the dense reservoirs wrapped around each nucleus and braided between them. The brightest complexes clump on kiloparsec scales but fragment into dozens of gravitationally bound cores at higher resolution. Where shear is high, those cores stall. Where converging flows cancel angular momentum, collapse cascades, and superstar clusters pop out in bunches. Polarization reveals ordered magnetic strands along the main dust sash and lifted into the wind cones, field geometry that helps collimate the outflow and shepherd cosmic rays. X-ray mosaics add the hot phase to the ledger. Patchy soft emission fills superbubbles above and below the lane, dotted with point sources from high-mass X-ray binaries that track the burst's most massive progeny. Optical spectra through the same chimneys show split lines and blue wings, signatures of shells and filaments accelerating into the halo. The momentum budget closes. Radiation pressure, supernovae, and stellar winds together are enough to punch long-lived vents without unbinding the entire gas supply. Some metals will escape to the group environment, much will fountain back after cooling, extending the star-forming window beyond the present blaze. Kinematics confirm the double heart. Integral field velocity fields show two rotating components, slightly misaligned and sliding past one another. Between them, a saddle of shearing gas feeds the brightest dust-shrouded H2 knots. One core sits behind thicker extinction and carries the richer molecular load, the other peers through cleared chimneys where feedback has already blown holes. The relative velocity and separation imply a mid-stage merger, past first passage, not yet at coalescence, with dynamical friction steadily shaving orbital energy. Extrapolate those curves, and the timescale to a single nucleus falls in the few times 10-year range, brief by galactic standards. Against famous analogues, the train wreck carves its own niche. It is more buried than the showy antennae. Much of the action is mid-IR and millimeter bright rather than UV flashy, yet it is more extended and less extreme than compact ultraluminous systems like ARC 220. That placement makes it an anchor point for theory. Models must recover not only the crooked lane and lopsided tails, but also the measured burst efficiency, cluster mass function, wind geometry, and multiphase gas fractions. When simulations get the orbit tilt and impact parameter right, they also match the observed burstiness and the way star formation hugs the shearing midplane, a strong hint that the underlying recipes for cooling, turbulence, and feedback are on track. Look ahead and the script is legible. Gas consumption and venting will dim the infrared blaze, successive passages will tighten the nuclei's dance, the central black holes, now drowsy, will feel deeper inflow and may pass through an obscured AGN phase on their path to pairing. Coalescence will erase tidy disk rotations via violent relaxation, leaving a pressure-supported body with faint shells as phase-wrapped memories of the tails. A retinue of hardy clusters will orbit as fossil witnesses. The once ragged dust sash will thin, radio halos will soften, and the remnant will take its place among massive, redder galaxies whose quiet light hides a turbulent youth. Call it the train wreck, the broken duet, the crooked spindle, the starburst anvil, the labels shift, the physics holds, gravity trades order for heat, shocks turn turbulence into stars, feedback sculpts escape routes, and dark matter cushions the whole performance. Study this system closely and you hold a decoder for countless distant mergers seen only as smudges, a local, time-resolved key to how encounter becomes transformation in the life of galaxies. Push the view to still larger scales and the shattered pair's influence leaks into its surroundings. Low surface brightness imaging teases out a gauzy envelope of starlight that blurs the interface between the colliding furnace and the intragroup medium. Within this halo, sprinkled filaments and knots betray bits of disk peeled away on earlier passes, each moving on a slightly different orbit that phase wraps into shells over time. If you map planetary nebulae or red giant tracers out there, their velocities sketch a transition from ordered rotation to a hot, pressure-supported sea, the future dynamical state written in today's outskirts. The crooked spindle is already teaching its halo how to forget the tidy memory of two spirals. Back in the core, The energy ledger balances across phases like a closed economy. UV photons from newborn O stars pump the photoionized zones, shocks from cloud collisions and supernova remnants top up the warm molecular component, hot superbubbles vent through the least resistant channels, transferring mechanical energy to the halo. Dust grains ride those flows, some sputtering to atoms in the hot bath, others surviving as sooty couriers that re-radiate in the far infrared as they cool. Even cosmic rays claim their share, diffusing along magnetic strands lifted into the wind cones and glowing softly in radiosynchrotron. The wreck's brilliance is not a single flame but a tiered furnace, each layer feeding and moderating the next. Time tagging the burst reveals its cadence. Spectral indices and cluster color magnitude diagrams point to a spiky history rather than a smooth blaze, brief, intense upswings keyed to paracentric tugs, followed by lulls as feedback overpressurizes clouds and throttles collapse. This burst-rest metronome is the audible version of dynamical friction's clock. With every pass the double heart loses a little more orbital energy, the gas finds fewer stable orbits, and the star formation peaks creep inward and grow more compact. The broken duet is not merely bright, it is rhythmic, a drumline of gravity and feedback beating toward coalescence. Zoom into the densest knots and the physics shifts to a contest between gravity and disruption. Massive clusters assemble inside overpressured cocoons where the sound speed and turbulence are high, yet radiative cooling and self-gravity still win on small scales. Protostellar outflows, winds, and ionization fronts erode those cocoons from within, regulating efficiency so that only a fraction of the gas ends up in long-lived stars. The survivors emerge with escape velocities large enough to resist tidal stripping, primed to orbit the future remnant as a metal-rich generation of globulars. Read their abundance patterns and you recover the chemistry of the burst, read their orbits and you reconstruct the encounter's geometry. The double-chord chrysalis also threads a quiet line through black hole growth. Gas losing angular momentum at kiloparsec scales must hand that loss down to parsec and then subparsec scales, a relay of torques that bars, spirals, and turbulence share. Right now the central engines seem modest, a whisper beneath the starburst choir, but the same inflow that fuels clustered youth is laying rails toward the nuclei. When the two massive objects finally bind, dynamical hardening will shake the central stars and gas, carving a core and perhaps flipping the balance of power so that an obscured active phase briefly outshines the fading starburst. The colliding metamorph is a case study in which light's first, stars or accretion. Environment keeps tugging at the edges. The wreck resides in a loose association where neighboring halos overlap and filaments of intergalactic gas thread the space between. Rambling dwarfs and faint companions stir the long tails, sometimes lighting pocket star formation within the debris. A close pass by an interloper can torque one plume, tweak the epicenter of returning streams, or even snip away a strand entirely. The broken duet is not evolving on a sealed stage, it is exchanging momentum and metals with a neighborhood that will remember the event in its own stellar archaeology. Against this backdrop, theory uses the train wreck as a tuning fork. Adjust the mass ratio and the tail's change length, dial the orbit's inclination and the dust lane kinks at a different angle, increase the gas fraction and the midplane pressure spikes, shifting the cluster mass function's upper cutoff. When simulations reproduce not just the silhouette but the star formation duty cycle, wind opening angles, and multiphase gas fractions, confidence rises that the same recipes can extrapolate to the distant universe, where individual clusters blur into pixels and dust turns fireworks into a warm glow on the cosmic infrared background. Take a final, patient look and the narrative resolves. The starburst anvil will cool as fuel is spent and vented, the double heart will slow dance into one, violent relaxation will remix stellar orbits into a spheroid with faint, rippling shells, the magnetic combing will relax, the radio halo will soften, the far infrared blaze will ebb to an ember. What remains will be a heavier, rounder system girdled by hardy clusters, an object that carries in its quiet light the whole biography of upheaval. Call it the train wreck, the crooked spindle, the colliding furnace, the shattered pair, the name hardly matters. What matters is what it shows, that galaxies grow by encounters that trade symmetry for structure, and that in the wreckage of two disks the universe forges something new. Even at human scales of observation, the shattered duet resists simplicity. Each new wavelength uncovers an extra layer, as though the galaxy insists on telling its story in many voices at once. In ultraviolet frames, the heart is blanketed by dust, yet arcs of hot blue clusters leak through, scattered like sparks. Optical exposures reveal the jagged dust sash slashing across the body, a wound stitched with H-alpha knots. Infrared images flip the script, making the hidden glow dominate, a furnace of heated grains. At radio frequencies, the cold gas reservoir sprawls outward, ghost-like and patient, tracing how far the collision's reach extends. X-ray detectors then catch the aftershocks, pockets of hot plasma and compact binaries, each a byproduct of stellar overproduction. Together, the spectrum reads like a polyphonic score, each instrument striking a different key of the same cosmic symphony. The wreck's appeal for astronomers lies not only in its fireworks but in its timing. Caught midway through its transformation, it shows both origin and destiny in one glance. The double nucleus is still distinct, betraying the two progenitors. The tails arc out as signatures of the orbital geometry. The central starburst rages at full tilt, yet the outlines of the remnant-to-be are already etched into the stars, a foreshadowing of an eventual elliptical form. To study such a system is to hold a time machine, past, present, and future collapsed into a single field of view. Cosmologically, the crooked spindle is a reminder that galaxies are not passive islands but migratory communities subject to gravity's restless pull. In the early universe, collisions like this were routine, the architects of mass assembly. Today they are rarer but no less instructive, fossils of an epoch when merger-driven starbursts lit up the cosmos. The train wreck shows in miniature what countless distant smudges represent, brief episodes of furious creativity that turn two disks into one spheroid, feeding black holes, enriching halos, and redrawing morphology in a few 100 million years. And still, despite the violence, there is artistry in its structure. The tails unfurl like ribbons torn in a dance, the dust lane curves like a brushstroke across the spindle, the glowing knots arrange themselves in constellations along bridges and ridges. Even in ruin, order emerges, patterns woven by the mathematics of orbits and the feedback of stars. That juxtaposition, destruction breeding symmetry, chaos sculpting form, is what draws observers back, frame after frame, simulation after simulation. The broken duet will not stay broken. In a future measured on scales far beyond human generations, the two nuclei will finally merge, the blaze of star formation will fade, the dust will settle, and a calmer, redder remnant will glide where once a wreck shone. But for now, it remains luminous in its disarray, a portrait of gravity mid-sentence, still writing the story of transformation in the language of dust, gas, and fire. As night sky catalogs record it under sterile designations, the battered system itself refuses anonymity. Through a telescope it presents a crooked spindle wrapped in shadow, but zoom deeper and the scene unravels into 1,000 small dramas. Molecular clouds collapse under tidal compression, birthing clusters that will live or die depending on how quickly their natal cocoons are stripped away. Winds from the earliest supernovae barrel through, carving cavities and sending shock fronts rippling outward. Those same shocks seed turbulence in surrounding gas, which then fragments anew, an endless chain reaction of star formation ignited by destruction. The whole structure is a feedback engine, where cause and effect loop together until the gas is spent. The hidden giants at the system's heart remain the most enigmatic players. Each nucleus, veiled behind curtains of dust, carries a central black hole likely weighing millions of suns. Though they slumber in comparison with quasar beacons, their gravitational pull already shapes the inflows around them. Gas spirals inward, occasionally flaring in X-rays as it brushes too close, a reminder that these engines can awaken at any time. In the distant future, their coalescence will send ripples across spacetime itself, gravitational waves that no eye can see but that sensitive instruments will one day hear, like a low bass note echoing through the cosmic web. Even the outskirts are restless. Faint streams peel away from the main body, curling into the dark like smoke trails. Some contain newborn stars, proving that even debris fields can kindle light when gas is shocked and squeezed. Others are populated mainly by older stars torn from their orbits, destined either to fall back and wrap around the remnant as shells or to drift forever into intergalactic space. These threads are more than decorative, they are dynamical fingerprints, recording the precise geometry and violence of the encounter, evidence written across tens of thousands of light-years. The train wreck is thus not a singular accident but a chapter in a universal narrative. Every massive elliptical galaxy we see today likely carries such a wreck in its ancestry, even if the scars have long since faded. By studying this one system, its doubled cores, its obscured furnace, its twisting tails, astronomers hold a cipher for decoding the past lives of galaxies across the cosmos. The lesson is clear: galaxies are built not in isolation but in collisions, not in silence but in bursts of light and chaos. And while the wreck's current blaze will last only a heartbeat in cosmic terms, the consequences will endure. Its enriched gas will seed future generations of stars, its massive clusters will orbit as fossils for eons, its merged black hole will anchor the remnant for the rest of cosmic history. Even after the dust lanes disperse and the infrared glow fades, the memory of this violent dance will live on in the structure and chemistry of whatever galaxy emerges. By any name, the crooked spindle, the shattered pair, the colliding furnace, the object embodies a paradox that defines cosmic evolution: only through upheaval does lasting order arise. From Earth's perspective, the fractured spindle looks frozen, yet in truth it is a slow-motion film, each frame stretched across millions of years. If we could accelerate time, the dust lanes would writhe like storm fronts, tidal tails would whip outward like banners, and the two luminous cores would spiral ever closer, tracing shrinking ellipses until they merge in a blaze of gravitational release. What we observe as a static silhouette is in fact a fleeting still from a kinetic ballet, one that reminds us of the deep disconnect between human timescales and the rhythms of the universe. The system's double nucleus phase is particularly precious because it does not last. Astronomers rarely catch galaxies in this act, long enough to be observable, but short compared to cosmic ages. That rarity is why NGC 520 is a touchstone. It provides a living example of what simulations predict but distant smudges cannot reveal. By dissecting its light, its winds, its clusters, scientists can tune models that explain how the universe's grand population of spheroidal galaxies came to be. The train wreck is thus both spectacle and laboratory, a natural experiment run by gravity itself. Even its obscuration, frustrating invisible light, carries meaning. The thick midplane dust is evidence of how gas is shunted inward, compressed and tangled until star formation ignites in hidden volumes. Without that dust, the blaze would spill unfiltered into space, but instead it is reprocessed, converted into infrared radiance that satellites capture as one of the galaxy's defining traits. This transformation, ultraviolet into infrared, chaos into glow, mirrors the broader theme: violence giving birth to luminosity, wreckage shaping order. If we could return billions of years from now, the scene would be unrecognizable. The dust sash gone, the tails dissolved, the blaze of star formation quieted. In their place would stand a massive, smooth remnant, reddish with aging stars, perhaps orbited by streams of globular clusters born in today's furnace. At its core, a single supermassive black hole would anchor the system, carrying in its gravity the merged legacy of two galaxies. What once looked like calamity would by then appear serene, a reminder that destruction and creation are only phases of the same continuum. Until then, the crooked spindle remains luminous in its disarray, a cosmic manuscript mid-sentence. To label it a wreck is apt but incomplete. It is also a forge, a crucible, a chrysalis. Each telescope that studies it adds another paragraph to the story, but the final chapter has yet to be written. Gravity is still drafting, line by line, in dust, gas, and fire. Seen through the lens of cosmic history, the battered pair is a snapshot of a process that has shaped galaxies across the eons. The Milky Way itself, though tranquil today, bears scars of smaller collisions, streams of stars, faint arcs of gas, that echo the same physics written in more dramatic form in this shattered spindle. To observe the train wreck is to glimpse our own galaxy's possible future, when, several billion years from now, it collides with Andromeda. What now looks like a distant curiosity becomes a mirror. One day our skies will blaze with tidal tails, our disk will twist and warp, and our nucleus will dance with another before merging into a massive elliptical remnant. The luminous chaos also hints at how galaxies feed their central black holes. While the stellar fireworks dominate, hidden flows of gas slip ever inward, losing angular momentum step by step. Today, those inflows are largely veiled, but the double heart is preparing for a climax in which accretion could briefly outshine the starburst. If so, the wreck will pass through an active nucleus phase, pouring radiation into space, sculpting outflows even stronger than the current winds, and perhaps leaving behind jets that etch their signatures into the intergalactic medium. The seeds of that transformation are already present, folded into the geometry of dust and gas we observe now. Even the smallest fragments of debris matter. Along the extended tails, dwarf galaxy-sized clumps of stars and gas take shape, tidal dwarfs born not in isolation but in the furnace of collision. Though fragile, some may survive as long-lived companions orbiting the remnant, fossils of the encounter's outskirts. These miniature galaxies inherit enriched material, meaning they begin life chemically older than most dwarfs of their mass, carrying the fingerprints of supernovae that detonated far from their birthplace. Thus the train wreck is not only building one remnant galaxy, but possibly spawning a retinue of satellites as well. In the grand mosaic of the cosmos, such events stitch together the visible architecture we see today. Ellipticals in clusters, lenticulars in groups, massive halos studded with clusters, all trace their ancestry to collisions like this. Every stream, every shell, every quiescent spheroid carries the memory of a moment when symmetry broke and gravity rewrote structure. By catching NGC 520 in mid-transformation, astronomers hold a rare volume of that chronicle still open, pages turning slowly, dust motes glimmering in the lamplight of newborn stars. And so the broken duet endures, luminous in ruin, eloquent in silence. Its story is not one of catastrophe but of becoming, a reminder that in the universe, endings are beginnings, and in wreckage lies the blueprint of renewal. Even its distance, so modest by extragalactic standards that we can parse individual clusters, turns the disordered spindle into a Rosetta Stone. Where high redshift smash-ups blur into single pixels and composite colors, this nearby collision separates into living pieces, embedded nurseries, wind-blown chimneys, filamentary bridges, and two distinct stellar disks that are being torque-twisted into one. Calibrate how dust soaks up ultraviolet light here and you gain the coefficients needed to reconstruct the hidden star formation in far earlier epochs. Map how the wind entrains molecules and grains in this colliding chrysalis and you get a template for the metal cycle that enriches halos across cosmic time. The broken duet also reframes how disks die. They do not simply stop rotating, their ordered motions are scrambled in stages. First, tidal impulses tilt and warp the planes. Next, gas streams interpenetrate with mismatched spins and cancel angular momentum. Finally, violent relaxation converts neat epicycles into a hot, pressure-supported sea. Along the way, resonant shells and ripples flicker into being as stars phase wrap on new orbits. Catch those fossils later, around a tranquil, reddened remnant, and you can read this entire upheaval backward, like rings in a tree that suddenly widened during a stormy season. On cloud scales, the train wreck proves that gravity is necessary but not sufficient. Turbulence, magnetic tension, radiative pressure, and supernova shock fronts all bargain over the fate of a parcel of gas. A core that would collapse in a quiet spiral might be shredded here unless converging flows cancel its residual spin. Conversely, gas that would drift for eons can be driven over the threshold by a passing shock. The result is a clustered mode of star formation whose efficiency spikes where shear loses and compression wins. That is why the brightest, dust-choked H2 knots huddle along the kinked midplane rather than sprinkling evenly across the system. The colliding furnace is equally pedagogical about outflows. The wind is not a single, ballistic spray, it is layered. Close to the midplane, warm ionized skins slide along the walls of evacuated chimneys. Farther out, a hotter, X-ray luminous phase fills biconical cavities. Stitched through both are filaments of cool, molecule-bearing gas accelerated by ram pressure and magnetic draping. Each phase carries a different fraction of mass, metals, and momentum, so the eventual fate of the ejected material, escape versus fountain, depends on where in this stratified flow a given clump rides. Follow the metals and you follow the future of star formation when some of that freight rains back. Even the debris fields are creative. Tidal plumes that look like mere wreckage host compact blue knots and, at their brightest nodes, self-gravitating clumps that flirt with dwarf galaxy status. These tidal dwarfs inherit pre-enriched gas from the colliding parents, so they are chemically old despite their youth. Whether they survive the remnant's tidal field is a matter of mass, orbit, and luck. If they do, they will parade for gigayears as living footnotes to the original encounter, satellites whose metallicities and kinematics forever betray an origin in violence rather than isolation. Meanwhile, the two veiled engines at the center keep time like metronomes with buried pendulums. Each pass of the nuclei knocks loose another tranche of angular momentum from the gas. Each tranche tightens the inflow, narrows the starburst, and raises the odds of a brief, obscured active phase. When the pair finally binds and coalesces, a single heavier black hole will sit where two once orbited, and the remnant core will bear the telltale scoured profile of stars jostled by a hardening binary. Somewhere, far below human hearing, space-time will have rung like a bell. Step back again and the crooked spindle resolves into a thesis about change. Disks are not undone by a single blow but by a sequence. Star formation is not a uniform drizzle but a syncopated drumline. Feedback is not a veto but a moderator. Dark matter is not scenery but the stage rigging that sets the tempo and absorbs the shocks. Call the object the train wreck, the starburst anvil, the ruptured spindle, the double-cord chrysalis. The names are masks for the same lesson, that structure in the universe is a negotiation between order and disturbance, and that the most enduring shapes often emerge from the most turbulent beginnings. And when the blaze finally dims, the record will remain in durable media. A halo of long-lived clusters will orbit as jeweled archives, faint shells will ripple in the outskirts like palimpsest writing, the central dispersion profile will remember how rotation gave way to pressure, the merged black hole will hold court at the core, a gravitational ledger of everything that fell inward. By then the colliding metamorph will look serene, but anyone who has studied this blazing chapter will see through the calm, reading in the quiet light the memory of dust lanes, shock fronts, and a pair of hearts that learn to beat as one. Even the way the wreck lights up depends on who is looking. Aim a sub-millimeter array and the scene is all cold breath and dense knots, CO and HCN lines sketching a braided river of fuel pouring toward the twin cores. Switch to integral field optics and you get a velocity tapestry, counter-streaming lanes, shock-broadened profiles, and small rotating pockets where gas has pooled into transient rings. In narrowband images the crooked spindle glows along the rims of its chimneys, H-alpha tracing expanding shells while, O3, flags the harsher edges where shocks and hard radiation overlap. Fold these views together and the train wreck stops being a silhouette and becomes an engine diagram, crankshafts, pistons, exhaust. The colliding duet's cluster population is a ledger you can audit. Mass functions tilt toward the high end, with dozens of superstar clusters tipping past 1010m, ages clump in bursts that line up with paracentric passages. Metallicities sit above those of typical dwarfs because the raw material is already enriched. A slice of these swarms will harden into true globulars. Their future orbits, some plunging, some grazing, will retain memory of today's geometry long after the dust sash has thinned and the tails have phase-wrapped into faint shells. The double-cord chrysalis, in other words, is minting tomorrow's archival system. Feedback, often treated as a single knob, is multi-threaded here. Radiation pressure nudges grains off cloud faces, stellar winds puff cavities before the first supernovae fire, then clustered explosions couple their momentum into the overpressured midplane, breaking through along fault lines of least resistance. Magnetic draping stabilizes some filaments against shredding as they're yanked into the outflow, letting cold molecular clumps hitch a ride hundreds of parsecs above the lane. Whether that freight escapes or fountains back depends on where it merges into the hotter, X-ray phase and how much help gravity from the dark halo provides. The starburst anvil is a teacher in how multiphase winds actually work. On the theoretical side, the shattered spindle is a calibration point for the whole merger playbook. Nudge the orbit inclination by a few degrees in a model and the dust lane's kink shifts, alter the gas fraction and the burst duty cycle changes, tweak the mass ratio and one tail fades while the other brightens. Runs that reproduce the observed infrared output, wind opening angles, and cluster demographics usually converge on a picture of a mid-stage, slightly off-center encounter, past first passage, not yet coalesced, exactly what the velocity fields imply. Get this one right and you earn trust to read the high redshift smudges where only totals, not details, are visible. The central engines keep time in the background. Today they're muffled, low-level accretion signatures rather than open quasar glare, but the same torque ladder that feeds clustered star formation is quietly stepping angular momentum downward. As the nuclei spiral in and the fuel line narrows to parsec scales, a buried AGN phase becomes likely. When the two black holes bind and harden, stars will be slung from the core and the light profile will flatten, a fossil of the binary's work. Much later, a single, heavier hole will sit at the center, and somewhere in the low-frequency sky a passing ripple will mark the moment the crooked spindle's two hearts became one. Environment keeps the script lively. The colliding furnace lives in a loose association where dwarf companions and filamentary gas tug at its outskirts. A minor flyby can torque a tail, trigger pocket star formation in the debris, or peel away a strand entirely. Some clumps in the plumes already flirt with self-gravity, tidal dwarf candidates that begin chemically old because they inherit enriched gas. A fraction will survive as satellites, circling the remnant for gigayears as living footnotes that reveal their violent origin through anomalously high metallicities and peculiar orbits. Project the timeline forward and the endgame is clear. Gas consumption and venting will dim the infrared blaze, successive passages will tighten the dance, violent relaxation will trade ordered disk motion for a pressure-supported spheroid, shells and ripples will briefly sketch the last beats of the merger before fading. Around the new, redder galaxy a retinue of hardy clusters will orbit like jeweled archives, while faint streams linger as palimpsests of the old disks. By then the colliding duet will look serene, but its quiet light will still encode today's turbulence for anyone who knows how to read it. Call it the train wreck, the crooked spindle, the colliding furnace, the broken pair, the labels rotate, the lesson stands. Galaxies change state not by drifting but by negotiating, gravity pulling inward, turbulence and feedback pushing back, dark matter setting the tempo, dust hiding the brightest sparks while recasting them in longer light. Catching this system mid-sentence gives us more than a spectacle, it hands us a decoder for how encounter becomes structure, and how, from two disrupted disks, the universe forges something enduring. Even the silence between its bursts is instructive. After each surge of star formation, the feedback-driven winds temporarily overpressurize the midplane, suppressing collapse until the gas cools and settles again. This staccato rhythm, peaks followed by pauses, gives the crooked spindle a heartbeat you can measure in tens of millions of years. Observers see it as stratified populations, newborn clusters still cocooned in dust, slightly older associations lighting up H-alpha arcs, and ancient survivors sprinkled through the tails. Stitch them together and the story reads as a stop-motion chronicle of the encounter itself. The debris fields are equally articulate. Long plumes arc into intergalactic space, their curvature encoding the geometry of the initial strike. Within them, clumps of gas condense into dwarf-sized fragments, a process that reuses the raw material of two spirals to spawn entirely new systems. Some of these, tidal dwarfs, may dissolve back into the remnant, but others will endure as companions whose metallicities betray their violent origin, tiny galaxies that are chemically older than their peers because they were born from already enriched matter. The wreck, therefore, is not just creating one remnant but seeding an entourage. On a larger scale, the halo of dark matter acts as both stage and safety net. Without its vast gravitational cushion, the two spirals would have flown past one another instead of binding. With it, orbital energy bleeds away and the pair remains locked in a decaying dance. Simulations show that the thickness and extent of the halo control the shape and longevity of the tails, as well as the timescale to final coalescence. In that sense, the invisible component writes as much of the choreography as the visible gas and stars. The train wreck is proof that what we cannot see guides what we do. Even its dust lanes, frustrating to optical eyes, turn out to be allies for discovery. By absorbing ultraviolet light and re-emitting in the infrared, they let astronomers measure star formation rates that would otherwise be underestimated. Space telescopes tuned to these longer wavelengths reveal the hidden blaze in its full intensity, confirming that the system belongs to the class of luminous infrared galaxies. That classification links it to a broader population across the cosmos, galaxies that build stellar mass in furious but temporary bursts, usually sparked by collisions like this. The crooked spindle is not an oddity, it is a representative, a nearby member of a much larger family. Project the timeline forward, and the narrative folds neatly into cosmic continuity. The two nuclei will spiral closer until dynamical friction and tidal torques bring them to coalescence. The burst will subside as fuel is spent or expelled, the dust will thin, leaving behind an aging stellar population, the tidal tails will fade into ghostly arcs or rain back as diffuse shells. In a few 100 million years, where once two star-forming spirals collided, there will be a single, massive, red-tinged spheroid. Around it will orbit a halo of hardy clusters, silent archivists of the wreck's incandescent youth. And so the battered spindle stands now as both chaos and prophecy. Call it the train wreck, the broken duet, the colliding furnace, the double-cord chrysalis, by any name, it demonstrates how destruction is only another face of creation. What looks like ruin is, in fact, the midwife of order, and what seems a wreck is really the blueprint of a galaxy yet to come.